Devansh? Okay. Yeah. So yeah, thanks, Devansh, for this introduction. And yeah, I'm Kshitij. I'm a grad student at Department of Physics and Astronomy at West Virginia University. And my research is also very overlapping with what Devansh mentioned. So use high performance computing and machine learning and algorithm development to search for astrophysical transients, basically. So, okay. So yeah, let's start with this. Let's start with the agenda for today. Just a second. Yeah. So yeah. So what is ML? And as Devansh mentioned, if you have any questions during this theory or the coding part, feel free to just message on Slack or on chat here, and we'll try our best to answer it whenever we take a look at the questions. So yeah. So what is ML? Machine learning, as it's said here, is the study of powerful techniques that can learn from experience. So typically, this is sort of how the terminology goes. You have artificial intelligence, which is a much broader field. And then machine learning is somewhat categorized within that as a sub part of it. And then deep learning is a further sub part of that whole bigger field. Higher level anatomy of this is you have some input, which feeds into a model or a function, and that gives you an output. The model itself has some parameters which can be tuned. So you can consider them as is written here as knobs on a machine. So you tune that knob, so you turn those knobs a little bit so that the performance of the model changes. And then with the same input and the changed performance, you get a different output. And you keep on tuning those knobs a little bit so that your output matches what you expect. So that has been shown here in this figure. You design a model. So you initialized or thought about a model, and then you created a model. Then you had some data. You feed that data to the model through which the model is updated. So it's either by fine tuning those knobs or changing some parameters of the model and things like those. Then you see if the performance of the model is good enough, right? So the model will give you an output. You compare that output with what you expected. You decide whether the model is good enough or not. If it is good enough, then that's great. If it is not, then you again go back to your data. Then you again go back to the process of updating your model a little bit. And then you repeat this process of checking if the model is performing well, or if it's performing what you expected, or if it needs any more modifications. So that's the sort of brief higher level idea. So there are some key components of any machine learning system. The first one being the data that we learn from. And I'll talk about all of these in the upcoming slides. So the first is the data that we basically learn from. That was the input, which we talked about. Then a model, which is actually going to transform this input to an output or data to an output value. Then there is an objective function, which tells you how good your model is performing. So in the previous step, I mentioned that you see whether your model is performing good enough or not. This objective function is what quantifies how good your model is performing. And then there is an algorithm which helps you to decide how to change the model such that it performs better. So once you know how good your model is performing, you want to make changes to your model such that it performs better. And this algorithm is what helps you to make those changes in your model. So let's talk about each of these four things in a bit more detail. All right. So yeah, data. It's the most important part of a machine learning system. There is no data science without data. You definitely need data to actually do something. It can come in many different forms. So here are just two forms which is written here. One is categorical. So for example, you have different colors which you want to identify. You have different genders, or you have different classes, for example, cats and dogs. But it could also be real valued. It could also be continuous. So for example, price, which can vary continuously, or height, or some other parameter which varies continuously and is not just categorical, which is divided into buckets or classes. Then there can be multiple issues with the data. So as with everything, each of these parts or each of these components of machine learning systems have their own tasks and have their own corresponding issues with them, which you have to be careful about. So potential issues with data can have some biases. Your data might have weird distributions. You can have distribution shifts and all those things. And we'll talk about some of these things in this and the upcoming sessions as we train more and more models. So now let's talk about the model itself. So model is, you can just imagine model, and I'll start from the second point and then go back to the first point. So model is basically just a function, right? It's taking an input, which is represented here by X, and it gives you an output, which is represented here by Y. So model, simply speaking, is just a function which takes some input and gives you some output. And as you can think about any mathematical function, there can be many, many different types of models. And each one can have a different specific task. So you have a particular application, and then you can design a model to give you a particular kind of output. You can have different flexibility in your priors. You can have different trade-offs. There are different models have different performances on different data. You can have overfitting issues and things like those. But the basic point is that the model takes in an input and gives you an output. So it maps an input value to an output value, and there are different kinds of models. Then there is this objective function. So objective function, as I explained, is something which gives you an idea of how good your model is performing, right? So objective function tells you how good, how well or bad our system is currently doing. So for example, what objective function is again a function, right? So it takes two inputs. One is the prediction, which your model predicted, and the other is the ground truth, which is basically the original values. And using those two, it compares those two values and gives you something which we call the loss, which basically tells you how good or how close you are to your actual solution. So we will see different kinds of loss functions, and the loss function basically is this f function here, or the objective function. There are multiple ways of calculating losses, and each has its own advantages or disadvantages or applications. And as I mentioned, this loss measures how far you are from your ideal predictions. So given a model, given some input, you make some predictions, then you compare those predictions with the expected predictions you wanted, and either you can subtract those, or you can do some complex functional calculation there to decide how far away you are from the actual predictions you expected. So that's what is meant by this objective function. And then there is the final part of the story, which is optimization algorithm. So once you have this objective function, which told you that, hey, this is the loss which you get after you apply this model on some data, now the question arises, how do I modify my model so that it performs better? And that task is done by this optimization algorithm. It tells us how to change the model parameters to improve the model. So the final aim with all this machine learning and everything is to make sure that our model is performing well, right? That's the goal which we want to achieve here. And this optimization algorithm is the final step, which tells the model, or which modifies those knobs or tunes those knobs such that the model starts performing better. So the most popular algorithm is the gradient descent, and we will code this and we will explore this much more in this session. And here is just a nice visualization that you start from. So you can just consider this map or this terrain as your this objective function, so the loss values, and you want to minimize this loss. So you start from a higher loss value, and then the objective function or this optimization algorithm tells you that, hey, you have to take this next step, next step, next step. At each step, you're calculating the loss, and you keep on moving towards the value where the loss is minimum. So you move from a mountain to sort of a valley where the loss is minimum. This is just a way of visualizing the loss. So there are primarily three types of machine learning techniques, which is supervised learning, unsupervised learning, and reinforcement learning. Supervised learning, as the name suggests, is supervised. So you give it, you train it, you give it some input and output. All of these require input and output, but supervised would require some training, and you have some base labels. Unsupervised does not have that information. And reinforcement learning is more of a dynamic system where you have an agent, it interacts with the environment give it some feedback, and then it modifies its behavior. So we'll primarily be talking about supervised and supervised learning, at least in this session, and we'll explore the others, I think, in the upcoming sessions. So what is supervised learning? This is when we have data on the quantity of interest, so labels. So for example, if you're doing regression, then you might have the prices of the data, housing prices based on the data set. So you have some houses, you have some features of those houses, but you also have what the prices of those houses are, right? And this price is what you wanted to predict. So you do have the ground truth values, and using those ground truth values, you can train your machine learning model. But if you want to do sort of a classification like task where you have images of dogs and cats, and you want your model to predict which one is a dog and which one is a cat. So you do have images of dogs and cats, but you also know which image contains a dog and which image contains the cat, right? So you do have the base labels through which you can train the model and tell the model that, hey, this image had a cat or this image had a dog. So that's again shown in this figure. You have some training inputs and you have some training labels, both of which feeds into your supervised learning framework, through which you train your model. And once your model is trained, now it knows that I have to classify stuff into dogs and cats, for example. So then you give it an input, for example, some random image, which it has not seen before, and it will give you an output of how likely it is for there to be a dog in the image or a cat to be in the image or something like that. And then, yeah, so the other is the unsupervised learning. There, you do not have the base labels. So you would not know which images have dogs or which images have cats. But then the task is also a little bit different. So this is more complex because you don't have the base labels. So we don't exactly know what we are looking for. So one example could be that you have many different chemical components. You have lots and lots of information about each chemical component, and you want to identify which components are similar to the other components. So you run an unsupervised clustering algorithm on it, and based on how similar different components are, it will cluster those things together. So just think of it like clustering. Similar things are bunched together. The things which are not similar are spread away. So you don't actually need to know which ones are similar or which ones are not. That information is provided by your, is sort of done. That information is conveyed to you by the clustering algorithm. So that's what is written here. You can still extract useful information out by looking for patterns. So one common technique is clustering, which I was just mentioning. The other is dimensionality reduction using different techniques. So dimensionality reduction is, for example, you have different features. You have tens to hundreds of features for each for each example. And you sort of want to visualize it in a nice way, or you want to extract only the major features which had most information. So you apply some dimensionality reduction, and as the name suggests, it reduces those number of features to a lesser number of features. And then you can work and apply other machine learning techniques on it, or do visualizations or data exploration. So in this session, we'll be primarily talking about linear regression. So for linear regression, again, for all of these things, you need these 4 steps. So first is the data. And here we have some tabular data with IDs, which are different examples. And all of these different columns correspond to different features of each example. Then you have some model. So here we have a simple model where X is the vector of input, so all those features. Then this W transpose and B are the weights and biases. So these are just numbers which we initially initialize as random numbers. And these are the ones which make your model. So this W and B is what actually is making your model. And this is what we want to train or what we want to modify. And Y is what the model predicts. So you give it an input X, it applies some mathematical operation, which is shown here, and it will give you an output Y hat. Then we have this objective function. Like I said, it gives you the loss or how good your model is performing. So Y hat was the prediction of your model. You compare that with Y, which is the actual values of your data from your data, or the true labels or the ground truth information. And you just take a squared value or squared sum of that to get the loss function for a given value of weight and biases. And once you know how good your model is performing, then you can apply this algorithm to modify the weights and biases. So here we are showing one such optimizer, which is called stochastic gradient descent. So here you had the loss function. In stochastic gradient descent, you take the derivatives of that loss function with respect to the weights and biases, and you modify the weights and biases themselves based on those derivatives, such that the next values of weights and biases will give you a better estimate or a lower value of this loss function. And typically, it's not done for just each example. That's why there is a sum here. You do it for a bunch of different cases, and then you average those things together. And that's what is represented by this B or beta and this sum. And then this N is just called the learning rate. And then we'll talk about all these things when Devansh shows you the coding example. But the basic idea is using the loss function and taking the derivative of the loss function with respect to the weights and biases. You modify the original values of weights and biases such that your model starts performing better now. And you keep on doing it iteratively till the performance of the model matches what you want it to do, or the value of this loss keeps on decreasing. So this is how it might look in action. You start from some random values of weights and biases, and then as you iterate over it, your predictions or your fit keeps on getting better and better. So then you might ask, why do we even need neural networks when this thing can work so well? Well, in real life, things are not linear, right? Things might look very weird. And this is just a two-dimensional example of which shows actually one-dimensional example, which shows how like things are not linear, right? You might have much complex nonlinearity in your data, for which you require some nonlinearity in your model, for which we actually require neural networks. So let's move on to neural networks now. Again, this was what I talked about earlier, which was linear regression. So linear regression can be also represented in this different way, wherein all these nodes or x's are your inputs, and they are connected by these weight values or beta. So each of this branch can be thought of as that w value or the weight, which gives you an output value. But then now in the case of neural network, you want to introduce some nonlinearity in your calculations because you want to approximate nonlinear functions. So think of it now as the neurons in your brain. You have some inputs, you have some body, and then these inputs can be approximated as dendrites or called as dendrites, and it gives you an output, right? So you had an input x that is being multiplied by these branches, which I already said are called weights. You apply that function x times b, w times x plus b, which is the bias. And then the final step, which is a very important step, which is you apply an activation function. That activation function is a nonlinear function. And I'll talk about it in 2 slides. So just wait and keep that activation function in mind. So basically, again, you're having some input, you apply a function to it, and that gives you an output. So, and you can have many such nodes and many such connections. So all these x's are your inputs. These h's are typically called hidden layers. Each of these branch represents a weight. And then you can have another layer, and then you can have another layer. And so you can keep on building this network of nodes, each connected by different branches called weights. And that's how your neural network sort of can be formed. So now coming back to that activation function I talked about, which is an important step. And so what you do, instead of just multiplying the x with w and then again multiplying with some other number, you apply this function, which is a nonlinear function. So for example, ReLU, which has this corner in it, or the step function, or the sigmoid. So as you can see, all of these are nonlinear functions. So after you apply the initial step of multiplying that x with a weight value and adding a bias to it, you apply this nonlinear function to it, and then you pass it on to the next layer. And then you again do the functional operation, then you again apply an activation function, and then you again pass it on to the next layer. So this introduces a nonlinearity in your neural network, which helps you map the nonlinear functions which we are trying to approximate using neural networks. So yeah, now I'll pass it on to Devansh for coding sessions.
Okay, so I strongly believe that coding is like swimming. You can't learn coding if you're just watching someone else do it. However, this is live coding. That means I will be doing this live over here. But if you want to do it on your own, there are comments and example in this notebook itself. You can mute me and keep doing your own thing, or you can just follow along. If there are any questions, feel free to ask me. And if you think that I'm going too fast, do let me know. Okay, so the first thing which we're going to do is we're going to use Google Collab. So that's Google's Jupyter environment, which is available for free to everyone. It also supports GPUs, which we may use later to train our networks. But for today, we can only work with the CPUs because we're not doing anything very computationally expensive. Now, the first thing I'll be talking about is a primer to PyTorch, because we will be using PyTorch for all these 6 sessions. And let's just step to this. So the 2 things which I want to the 2 key things which I want you to learn from this session about the primer is one, Torch has tensors very similar to how NumPy has arrays. And the other thing is which Torch allows you to do is it allows you to take gradients, which NumPy doesn't. So the first thing which needs to be done is just import Torch and import random. This is probably going to stay standard for all of the 6 sessions. Just also importing PyLab because we want to visualize things at some point. Now, the first thing I'm going to do is create a tensor, which is torch.rand with a size 3,4. So what it's going to do is it's going to create, is this connecting to the instance? Give it a second, and it's connected. Okay. Didn't import torch. Anyway, So the first thing it's going to do is create something called my tensor. It's a tensor object, which is of size 3 by 4. So 3 rows and 4 columns, and it just gives you some random values. When you run it, you probably will get different random values because it's random because of this rand over here. Now, this is very similar to NumPy arrays if you've used NumPy arrays before. If you look at the type of this, it's going to say it's a torch.tensor. And this is a float32D type. Now, you can also try using torch.randn. So this is going to give you random normal. So let's just try that, torch.randn. And we can again do 3, 4, going to give you another set of another tensor which are normally distributed. Now, the cool thing about PyTorch is that it allows you to do gradients, and let's see what that means. What I mean by that. So I devised 2 tensors, which is A and B, and this is just two normal values, torch.tensor4 and torch.tensor12. I've added this extra keyword called requires grad is equal to true. And what this does is whatever operation we'll do on A and B, Torch will keep a track of that. And then it will create and it will calculate gradients. So right now, if you just do A and B and print A and B, it's just going to give you 4 and 12 because we haven't done anything to it. But it also tells you that for both A and B, we have required the grad to be true. If you compute gradients right now, it's none because we haven't done any operations on them. But let's perform an operation, a very simple mathematical operation where y is a cubed minus b squared. So here's y, and if you print y, it's just minus 80, which is fine. It also gives a grad function which says subtraction backward 0. That means we took these numbers and we subtracted them. We also did some powers. We also raised them to some powers. Now, what we can do is we can take gradients of this y with respect to A and B. So we can compute this del y by del A and del y by del B. And the way it's done is using just dot backward. So you can just do y dot backward, and it computes the gradient. It doesn't show you anything, but once you do A dot grad and B dot grad, it's going to give you the gradient values. And you can actually compute them by yourself with hand and see if these numbers match. Now, we can try the same thing with another function over here. We can try something like y is equal to torch dot sine and then A plus B whole squared. And then again do a torch or y dot backward. And now when we look at the gradients, it should be A dot grad. It's going to give you some value over here. You can similarly do B dot grad over here. It's going to give you the value for the gradient. So we'll be using this because remember, Kshitij talked about stochastic gradient descent. We will be defining a loss function at some point later in this notebook. And then we'll take the gradient of that loss function with respect to our weights and biases. So that's what we'll be doing later. And that's why this y dot backward and this A dot grad and B dot grad will come. That's where all these things will come in handy. Now, so the first thing to do is linear regression. What our model looks like is something like this. So we have y hat is W transpose X plus B, where X is your input feature, B is your bias, W are your weights. And the first thing we'll do is write up a function which will take these as the inputs and give us the model output or the y hat. Now, so this is okay, yeah. So this is very simple to do. All you need to do is torch.matmul, which is a matrix multiplication between X and W plus B, and that's it. And this model, when we pass W and B such that W and B both require gradients, it's going to take care of this whole thing. It's going to be able to take derivatives, and that's what we'll be using soon. So the next step is to generate some synthetic data. We'll take a very simple case. This is exactly how it is denoted in d2l.ai book. So you can follow that, or this is the same thing. We'll take 2 input features. That's why the W will have these 2 values and the bias, which is just another number over here. And we'll write a function which will generate our synthetic data. Now, in real world, whenever we measure anything, our sensors have noise, and that's why We'll also be simulating some Gaussian noise on top of all this data. So we'll be using, again, torch.matmul to create our data, and then torch.normal to add some noise on top of it. So let's go ahead and do it. So we need some X values first. So we need torch.normal, and we need, so you can see we need 0, mean, and unit standard deviation. And these are just our X values. And the shape which we want is number of examples, comma, length of W. So that's our X values. The Y value which we want is now similar to our models, which is torch.matmul. There's X over here and W plus B. Now the next thing to do here is to add some noise to it. So this torch.normal, and you can add 0 mean and then 0.01 standard deviation. And the shape has to stay the same. So you can just say y.shape over here. And now we can just return this X values, and the Y, we will reshape it to -1, 1. So that's what. So that's a very simple function which will take in, given the weight and the bias and number of example, it's going to give us some data which is X and Y over here. So we'll now generate data with true W, or the ground truth, as 2n minus 3.4, and the true B, which is the intercept in this case, or the bias, is 4.2. And we'll generate 1,000 examples. So let's see how data looks like. Sorry for that. Just went to the bottom of the notebook. Okay, here we are. So set on the code. So let's look at the features. This is what it looks like, and the labels. And this is what labels look like. That's fine. It's a one-dimensional array for the labels, two-dimensional array for the features. That's what we requested it to do. And that's what we have over here. So we can now visualize this. So that's why we imported plt dot, so mat.lib as mat.lib. And we can just, so we have two dimensions, and the weights, if you remember, were one of them was positive, one of them was negative. Let's see what it was. So yeah, 2 and minus 3.4. Okay, so this is what the two features look like. One of them is positive slope, one of them is a negative slope. And this is what our input data is. So the next thing which is given to you here directly is a data iterator. What it does is it takes your data, which is your features and your label, and just converts it into an iterator. So we can talk about iterators later on if there's time. But the short story is as follows. Most of the time when you're trying to do machine learning, your data is so huge that you can't just load it up on your RAM. So we divide this data into small chunks, and then we use those small chunks to train our machine learning models. And that's what this function sort of does over here. So batch size, we generated a data which has 1,000 samples in it, but we'll go with a smaller batch size. We can take a batch size of, let's say, 15, 20, or anything. And then this is just your input and your output. So let's run this. And let's see how this the data iterator works. So we create a new variable called data generator, and it's data iter batch size. Let's call it 25 for now, and then features and labels are the same. So features is features, and labels is labels. So this data generator over here is an iterator. So if you just print this, it's not going to give you anything. It's just going to say it's a generator object. So to get some features out of this, there are a couple of ways of doing that. The easiest one is, let's call it batch features and batch labels. And now we can do the same exercise again. We can plot them. See how it looks. So it just gave us some chunk of the data. It didn't give us everything. Just 25 points out of this whole sample. And that's what we'll use in our stochastic gradient descent. We'll take small chunks of data, we'll compute the loss function on this, and then we'll compute the gradient and update the weights. So let's come to the loss function. So the loss function is as follows. You have your y hat, which is the prediction coming out of your model, and you have your yi, which is the ground truth. And what we return is just a mean squared error. So it's a very simple function. You can just do return 0.5 y hat minus y and whole squared. Now, the next step to do is to actually take gradients of this loss function, which we just created with respect to our weights and biases, and we'll use that to update our weights and biases. So let's see. The first thing we need to do is this. We need to define a small learning rate, and we need to initialize some values for W and B, which we'll learn. So we had our true weights and biases, but for our machine learning model, we'll initialize some random values, and then we'll see how that goes. So we put in a learning rate of 0.001. We typically use a small learning rate because we don't want to jump around a lot in our in this loss function topology. For our weights, we'll just do torch.rand, and it's a 2,1 shaped tensor, but we require the grad to be true because we will be updating these weights. Similarly, we have the bias values. So that's a torch.rand1, and again, require grad is equal to true. And we can print all these values and see how this goes. So, yep. So we initialized our W to 0.1 and 0.2. This is far away from our ground truth. And similarly for the B value, it's 0.9. But in both of the cases, we have required is equal to true. So the next step is to actually write the training loop, and this is the bulk of training. So this is the bulk of the work for all this. The first thing over here is for epoch in range 50, and what I've done over here is, I'm just going to shorten it to 5, is we're going to take all of the data, we're going to split it into small chunks, and we're going to compute, we're going to pass it through our model, compute the loss function, and update the weights using this equation over here. So the weight, the new weight will be the old weight minus the learning rate divided by the batch size times the gradient, and similarly for the bias. And we're going to do it over and over again 5 times. That's the epochs over here. So the first thing which we need to do is we have set a batch size of 100, and features and labels are the data which we have, and this X and Y will become our sort of batch features and batch labels. So the first thing you need to do is you need to put these features inside the model and see what the output values are. So you can see output is equal to model. This is what we had defined earlier, which takes in the X value, the W value, and the B value. And once you have this output value, we now will compute the loss. So the loss value is equal to, something went wrong with the keyboard. Okay, yeah, it's working now. So the loss value is this loss function, which takes 2 values, y hat and y. So y hat is the prediction, which is output, and y is the actual value, which is which is the ground truth, which is the batch prediction, which is the batch label over here. Yep. And now the next thing which you have to do is to take the gradient, and from the primer, remember, all you have to do is just do a dot backward. But before we do that, the loss function right now returns a vector. It does not return a scalar value. So you have to add a sum to it. So now the loss function will be a scalar value. What you can do is also you can print loss and see how it goes. Right now, if I run this, since we're not changing anything, it's just going to give us the same. Wait. Oh yeah, so we are running it for different batches. That means for different, but for same W and B. So this is going to give us some values for the loss, but at all times we have some backward. That means the grade. That means there's a gradient function. It knows how to compute the gradient. So we can now just do loss dot backward, and this will allow us to take the gradients. The next step is important. This is what you have to do with all the PyTorch models, and this is with torch.nograd. And the reason we do this is as follows. Any operation you apply on W and B will be remembered and will be taken care of while you're computing the gradients. But we do not want to remember this particular operation, which is how you are updating the weights. So this is why we say torch.nograd. This is where you say, okay, just update the values, but don't count this while taking the gradients. Otherwise, what PyTorch will do is it will keep track of this as well. And the next time you take gradient, it's going to take the gradient of this step and the model, which is not what we want. Okay. So now we update our values. We say W minus equal to our learning rate times W.grad. And this divided by length of Y. This length of Y is just the batch size. We do the same thing with bias. So that's learning rate times B.grad divided by length of Y. And the next step is also what you have to remember, which is W.grad.0. And I'll explain this in a second. 0. Okay, so once you have computed the gradients, you don't need them. Once you have computed the gradient and used them to update the weights, you don't need them anymore. So what you do is you set the gradients to 0. And in PyTorch, whenever you see an underscore somewhere like this, what it means is that just do this thing in as an in-place operation. That means when you say W.grad dot 0 underscore, just make the grad values to be 0. So what's going to happen is for an epoch, it's going to take your data, split it into 10 batches, each of size 100, put all of those 100 values in the model and give you an output, compute the loss, and we'll print the loss value over here. And then we do so we do loss.backward to compute the gradients, and then use those gradients to update the weights, and then set the gradients to 0 again for the next loop. So now let's run this and see what happens. No, sorry, it's supposed to be Y. And let's not print loss at the end of every batch. Let's just print at the end of every epoch. So what you can see is that the loss function is decreasing. This is what we were talking about, that we want to move in a direction where the loss keeps going down and down. So if we run it for longer now, it's going to keep running. It's oscillating a little, but it's going down. And now we can print and we can compare the values of W and the weight and the true weight, and similarly the bias and the true bias. So it's still off. Looks like I've made a mistake somewhere.
I have a question.
Yep.
Can you repeat again why we need torch.nograd again? I missed that part.
Okay, so
Thanks.
The reason you need torch.nograd is because when you're trying to do this operation over here, which is update the weights, you don't want torch to remember this operation, because whatever operation you do on W, torch will remember that and use that to compute the gradient. And we don't want this operation to be counted while we are taking the gradient. So we only want the gradient of the loss functions and not the updating method. And that's why we put all these things under torch.nograd. Does that make sense?
Sorry, still, I thought you did grad.0. Does that already clear? Doesn't that already clear all the gradient?
Oh, so these are two different things. So
okay.
W.grad.0 and B.grad.0 will set the gradient value to be 0. Okay,
right.
So that's one thing. The second thing is PyTorch knowing how you use your W's and B's. So for example, if we go back to the top, to the primer itself. Okay, just give me a second. Yeah, here. So we defined two tensors A and B, and we said require grad is equal to true. And then we perform this operation, a cube minus b squared. And this is what Torch will remember, that you used a cube and b squared. And then when you have to compute the grad of y, it knows that you have done a cube over here, and it has and you have done b squared over here. And that's how it computes the gradient. Now it knows what operations you have done. Okay.
Right.
Now, when we are updating the weights, we don't want that operation to be counted for gradient calculation.
Okay, I see.
Yep.
Cool.
So that's fine.
Thank you.
But the question is, no worries. The question is why is our linear regression not working? Let's see. Let's try it again with some new values. It is going down, but not as much as we would like it to. That's not going to be very. Wait, did it not update? So the original value, okay, it's not updating the values for some reason. Let's see. So our W values are 0.251 and 0.38, and that's what we are getting out. For some reason, our values are not getting updated. Yeah. Any suggestions, anyone? Okay, let's try changing the learning rate to slightly higher, and we will ask it to print W and B at each step. Okay, printed a lot of things. So the values are changing. This is W and this is B, and I can see B values changing. The W values are not changing that much.
Is your loss function okay? Maybe the loss function is some typo.
Now the loss function looks fine. It's just this, and then we do a sum at the end. And then we compute the loss. Okay, let's run it for one and print w.grad and b.grad. Check it. It's coming back. So let's see. So that's W and B, and then these are the gradients. So let's see, this value in 2.001 divided by a batch size of 100 will make it really, really small for it to change. So let's do. Okay, so let's try something else. Let's run it for longer. and with a
Is the
smaller
loss,
bits.
loss function supposed to reach 0?
The loss function is supposed to reach a minima, not 0 exactly.
Okay. The loss value, sorry.
So we initialize these, and now let's run this. Let's see how it goes. Oh, there it is. So that worked. Okay, so what I changed was two things. One was let it run for longer, and second is run for a smaller batch. So what was happening was the length of I, which was 100, and the learning rate, which was 0.01 times the gradient, which was making the update to be very, very small. And that's why it was changing, but it was changing at a very small pace, and just sort of tuned a few things to make that better. So it started with like 19, and you can see how quickly it has gone from like 19, 3, 0.4, 0.07, and then goes back to like single digits over here. So yeah, now let's compare the actual value and the true value. So that's 2.002, and then that's 2. This is minus 3.4-ish, almost. So we are able to sort of recover whatever we have injected in this. And this was the very simple case. This was linear regression. If you have, I can take questions at this point, and can move to neural networks after that. So any questions?
Yes, hello. Yes, please, could you explain again why do you divide the gradient by the length of what I imagine is the number of cases in the batch, the length of y? Why
Yeah,
do you
just
divide
take
the gradient?
you just take an average over the batch. So what you do is you take some part of the data set and see what's the average loss in that case, and that's why there is the sum over here, and then divided by the total number.
Okay, so the gradient by itself would be like the sum of the gradients for each data point. Is that so? If we don't divide it, what we will have in the gradient is the sum of the gradients?
So actually no, because the loss is a scalar. So the moment we have already done our sum at this stage. So that L of I, and all you do is you have basically this thing. You have this loss function, which is y hat I minus y of I for the ith point in your data, and you just sum all of these together, and whatever number you get in the end is your loss for that batch, and then you just take the gradient of that. But to do that gradient, actually, yes, this is what Torch will remember, that you did a sum over all these things. You took a square of all these values, and that's how it computes the gradient. Does that answer your question?
Let me think a bit. So yeah, so the gradient is over the sum. So it takes the gradient of that sum.
Yes.
So what would the gradient represent if we didn't divide it by the length of y?
Yes, it's like an average gradient over that batch.
I think he's asking if we do not divide it by n, then it would be just the gradient of the sum, right? But we want the gradient of the average of the batch, and that's why we divide it by n, right?
Oh, okay. Yeah, thank you.
So
yeah,
so what Devansh was saying is that if you just ignore this 1 over n in this summation in the first equation, then the gradient which is being calculated there without the division would be just the gradient of this sum. But because we have a batch and we do want the average gradient over that whole thing, that's why we divide it by 1 over n, or basically divided by n, which is the length of the sample, length of the batch there, right? I think that's what your question was.
Okay, thank you.
Yeah. Okay, so if there are no more questions, I'll move on to the next step, which is an extension of this. So this was a very simple model. This is a very simple data as well. We do have just linear features over here. We have two features, and then some labels which are here on the some labels which are here on the y-axis. But let's try to create a multi-layer perceptron which will try to fit this data. I do want to put a caveat over here. This is a linear problem over which we are trying a nonlinear solution. This is just for the sake of simplicity. We are doing this in the book. They try to do it with the MNIST data set. Feel free to try that. And if you have any questions, we'll be happy to answer that over Slack. But given the time constraints, we'll be just trying to run a really small neural network on the same data set over here. So for that, this is what our task is. So we want to compute these prediction values. We have the same weights, feature vectors, and bias. The additional thing which we have now is a nonlinear activation function, which is the ReLU, which is given as max of 0, x. This is what Kshitij had already shown in the slide. So anything which has a negative value will get replaced by 0. Anything which is positive will just stay as it is. And instead of just computing the first thing, which was W transpose X plus B, which was our original y hat, we'll now just put that as an argument to our activation function. Now, the neural network which we'll build will take 2 inputs because we have 2 features. For the beginning, we'll take to begin, we'll take 2 hidden layers, and the first layer will have 10 neurons or 10 units, and the second one will have 5, and both of them will have a ReLU activation function. Now, for simplicity, what I've done is I've added 2 functions over here. One is ReLU, which is, as it said, just max of 0 and the input, and the other one is update params over here. So this loop which we wrote over here, this part over here, this is good to do if you just have like a couple of parameters. But as you'll see over here, now we'll have a lot more, and we can just replace it with another function, which will do our job over here. Okay, so now the thing to do over here is to basically fill up these things. We have 10 hidden units in the first layer, 5 hidden units in the second layer. So we have to initialize weights and biases for all of them. Now, this is where things get slightly tricky as well. And the reason for that is as follows. Linear regression is a very easy, simple model. You can see what's going on. You can compare the W's and B's. But as you start coming to deep learning, as you start coding up these neural networks, it becomes much harder to interpret and see what's going on. They start becoming more like black boxes. So we will be defining these weights and biases, but we won't be able to compare them to the original values. The only thing which we can actually compare is see how this network performs as compared to our linear regression model. So the first thing is the W1, W2, and then we'll have W1, W2, and W3, and similarly 3 biases. So the first one, we have 2 input features, and the shape would be 2, hidden units 1. And remember, we'll always have to keep require grad is equal to true, because these are the parameters of our network or the model which we have to learn. So and for the bias, same as the number of hidden units. So that's hidden units 1. Now this will map to the second layer. This will be hidden layer 1, and then hidden layer 2 over here. And similarly, just like the first one, this will be hidden layer 2 over here. And this is the last layer. This is what will map our hidden layers to final output. So hidden layer 2, 1, and finally 1 as this. So we'll now create our model, which will look something like this. So the first thing we need to do is we take in our, so for the first hidden layer, so hidden layer 1, we'll do torch.matmul x comma w1 plus b1. And now this will serve as an argument for the relu function which we defined over here. Let me just check. Yep. That's our first layer. The second layer will now become hidden layer 2. So hidden layer 2 will also have a relu function in it. It will do torch.matmul again, but now the input for this case will be from hidden layer 1, and then so that's hidden layer 1, and then w2 over here, and then we'll add b2, and then finally there's no activation function at the last layer, so it's just torch.matmul. The input is hidden layer 2 comma w3 plus b3. One of the things which you can see over here is that I am using w1 b1 w2 b2 and w3 b3 over here, but I have not put it in the function definition. Python does this trick where anything defined above a function is automatically inherited inside, so you don't have to put it here and it just works. The other thing which I have done here is I have created a list of all the parameters, and the reason I've done this is because we can use this function over here, update parameters, to update all the parameters at once. So what this function will do is it will step through the list and compute the gradient and use a learning rate and then again the length of batch to update the parameters. That's what we'll do over here. The next step is now again to create the training loop. This is going to stay very similar to what we did earlier. So we can just do output is equal to model X. Wait, let me run this. Right. So output is equal to model X. Now loss is equal to, we'll use the same loss function as earlier. So that's loss function, our output value, and the ground truth, and then the sum at the end. We'll again do loss dot backward, and then params is equal to what's the function called? It was called update params. And then just put params in again. We will print the loss value to see how it goes, and so now make this small again. So now before I run this, let's just go over it once more. So what's happening is we have two input features and they get mapped to 10 hidden units. So that's why the shape of W1 is 2,10. And the bias will have the same shape as the hidden units. So that's that. We are just randomly initiating all of them. And then here's our model. You take your input, multiply it by the weight at the biases, give it to ReLU. Use that as the input for the next layer. Multiply that with weights, add the bias, and again, put the nonlinear activation function, and then use the output from here as the input of the last layer, which will just give us one value in the end. And that's what we have coded up over here. So now let's run this and see how this goes. You can see the loss values are decreasing. The loss values are not as small as we had seen for.
Just a quick thing, sorry. I'll scroll back up. Yeah, and I think someone has sent that on chat as well. There is a typo in the model definition. If you go to the model function, it should be hidden layer 2 instead of hidden units 2.
Oh, yes.
And then again in the return, it should be hidden layer 2.
Yes, yes. Thanks for pointing that out. Hidden layer 2. That should fix it, I guess. And now let's run this. So, yep. Runs, the loss function sort of keeps decreasing. And yeah, so that's what we just did. We just created a really small neural network with 10 and 5 hidden units for the 2 layers with a ReLU activation function. And we just trained it on the same data. The way to compare this model with the first model is just to compare how the loss is. So in this case, the final loss was about 0.007. Don't remember what the minimum loss was for the linear regression model. But this is just for like demonstration purposes. Now, to end, we're also going to show you how you can create a really simple neural network or a multi-layer perceptron in PyTorch. This is something what we use in our everyday lives when we are creating neural networks. So all you do is torch.nn.sequential, and then it's really simple. All you do is torch.nn.linear. So 2 inputs which go to 10 units, and then add a ReLU. Then the 10 go to the 5, add another ReLU, and then finally this 5 go to the 1, and that's it. So you don't have to sit and initialize all the weights. You don't have to write all these functions by yourself. It's already pre-written with Torch, and this is how you create a really simple neural network. You can run this as well. And if you print net over here, it's going to just tell you that this is what it has. So it automatically adds the bias values. That's why it says bias is equal to true. Input features is 2. Output features are 10, which goes in here. Now the output features are 5, and then they go to the final layer, which has output feature of 1. And we added 2 ReLU activation units in between. Everything has a bias. Now, the loss function, which is what we were using, mean squared error, is also sort of pre-written in Torch. And all you have to do is just this, torch.nn.mse loss. And then reduction is equal to sum is literally what we were doing by calling dot sum at the end. Now, that's your loss function. And this is your optimizer. So we wrote our own stochastic gradient algorithm, or a little stochastic gradient algorithm using this update params function over here, where it does torch.nograd. It updates each parameter value by multiplying it by taking the gradient and multiplying it with the learning rate, and then sets the gradient value to 0 at the end of it. And all of that will now be done in a very similar loop. So what you do is you do trainer.0grad. This is what our trainer is, and that's our optimizer. You initialize everything so that it has 0 gradients. Now you take in your data, give it to your network, and compute the output. Use that in your loss function, which is torch.nn.mse loss. In the exact same way, do loss.backward and trainer.step, and that's it. And it's done. That's how you do it in PyTorch. We can run this again. It's going to wait, trainer is not defined. Okay. Should run now. Gives us some values. I think this can be tuned, the learning rate, and there are many other things which can be tuned in this case to give us the similar performance. So that's all I have in terms of the coding session for today.